Okay, so let's get started. Welcome to lecture number 16 of the course. And we more or less start where we had stopped in the last lecture. So we're still working with operator learning. So which means that we have a abstract PDE of this form. And we are interested in learning the solution operator. The operator G that maps the inputs X to the solution of the PDE Y, right? So this is the basic idea. And so far, we have seen a whole plethora of operator learning algorithms, whether it is CNNs or DeepNet, FNO, CNO, and so on. They have different features, different attributes, different strengths and weaknesses. But the point that we have been doing is in the last lecture was to look at what are time-dependent problems. And this would be the starting point of today's lecture. So what is special about time-dependent problems? So first of all, this relies on time-dependent PDEs. So that's the first thing. And the abstract form is given by this, right? So this is the abstract form. So perhaps in the last lecture, I did not mention it explicitly, but a typical example would be the heat equation. So you have ut minus Laplacian of u equal to 0, and u at x0 is u naught of x, or u bar. So this is a typical example of a time-dependent PE. Another typical example, which a priori is not in this particular form, is given by the wave equation. So this is the heat equation. But if you consider the wave equation models the propagation of waves in different media. Let's say for a uniform medium, so utt minus Laplacian of u equal to 0, u at x0 is some, I should have said v perhaps. Okay, because sorry for the notational confusion. So we are dealing with the wave equation just to illustrate the beast that we have to confront. And here the displacement vtt is equal to or minus Laplacian of v equal to 0. V at x0 is some v bar, and vt at x0 is equal to w bar. So a priori, it doesn't look like that this equation here, the wave equation, is fitting this format, right? But of course, many of you perhaps know this. There is a simple trick by which you can put one in the form of the other, and the trick is simply to identify what is called the velocity vt with a w. So then you can rewrite the equation as ut equals to, vt is equal to w, and wt is equal to the Laplacian of v, right? And then you got back in this form. So you can write even high order time derivatives in the form of first order time derivatives by simply expanding everything into a system. In other words, your unknown now, is v and w. So that solves the problem. So any time dependent PDE can be written in this abstract form. Good. So what is the solution operator? This is what we were looking at in the last lecture. So the solution operator is now a mapping which takes into account not just the functional input, but also the time. So time t is one of the inputs to this solution operator, and it churns out the solution at a given time t, given that you input t and the initial condition, right? So this is what determines the whole thing. So if you think in terms of data, so what you have is trajectories. So in other words, of course, ideally we would like to have the entire time history of the solution. We would like to have ut for t greater than 0. But of course, in practice, we have to sample them at discrete points. Nothing on the computer can be continuous or continuum. So as a consequence, what you do is that you start at the first time step, the 0th time step, the first time step, and so on and so forth. So whenever you generate data numerically or through observations, what you really have is this kind of a, let's say, a trajectory of the solution, right? So what is the learning task, as I said? So and this is very, very important because not every algorithm fits into this framework, but that is what is essential, because when you think of a solution operator of a time-dependent PDE, all that you do is that you give it the time and you give it the initial conditions, and it churns out the solution at that particular time. Okay, and this is what I expressed here, that if given the initial conditions, boundary conditions and so on are the inputs to the PDE, you have to generate the entire trajectory. the entire solution trajectory for all times t. So this is sort of the basis of this entire method, that you have to generate the entire trajectory. And as I explained in the last lecture, you could do it with neural operators. You could have used either direct or autoregressive evaluation, and this was not efficient in any way, shape, or form. So what I had stopped with in the last lecture, and which is what I want to start with again, is to use what is called lead time conditioning. So this is the principle here, that you have to give time as some sort of input channels everywhere. So let me try to explain that a little more. I was a bit hasty in the last lecture. So perhaps we can do this. So here is a typical example. So you have CNO. This is just an example. It could be FNO, it could be DeepNet, whatever. And you remember that we have a sequence of layers which are stacked up together as in any neural operator. So you start off with the input and then you have these convolutional layers, you have these residual layers, and so on and so forth. So what you have to do now in lead time conditioning is first, and this is perhaps not as important as what you have to do second, but nevertheless, you have to provide the lead time itself as an input channel. What do I mean by that? What I mean is that in the set of inputs, apart from the solution, you also have to provide the time. So in other words, let's think of this neural operator as some S star. You have to give it the time and you have to give it the input, right? Just like we did with the solution operator, because in the solution operator, you have to provide it with the time to be able to output the solution at a given time. So this is part for the course. You need it. Good. So that is, as I said, for instance, you try to give the time, you try to give the solution at some earlier time, and then it can produce a solution at a later time. So this is at the very beginning itself. But remember that what we are doing is that we are stacking up lots of layers. So even in a CNO, some of the largest models that we have, we could have anything between 20 and 30 layers. So what happens is that if you only give time as an input at the very beginning, there is a potential that the effect of this time is not properly propagated, right? It has to take into account time, it has to take into account initial data. So time is just an additional channel. So this is an additional channel. It has to take into account the input data, it has to take into account various things. So what happens as a consequence is that you have to somehow keep the information about the time in subsequent layers. And this is where one has to add or one has to modify what are called normalization layers. So remember that at least in the practice of deep learning, in the tutorials you have seen it, that you always have to normalize data, right? So whenever you have to give an input to the machine learning system, in order to sort of reconcile the different scales, in order to enable the gradient to propagate smoothly. So what one does is that one tries to normalize the inputs, let's say between -1 and 1. This is a typical range for normalization. Now what layer normalize, or so this is what you do at the level of the input, right? But what one does also is that after each layer, you keep on normalizing, because the output of the layer can be whatever. So you normalize it so that you have better gradient propagation properties. So you have different kinds of normalizations. I'm not going to define, later today I'm going to define one of them explicitly, but you can do it over the instance, over the whole sample. You can do it over the batch, you can do it over the layer. There are different ways in which you take normalizations. So in particular, just imagine that in the time independent case, what you do in normalization is that you take the output. For instance, you take the output here of this particular layer, and then this is what happens, right? So you take the output and you take out the mean. So you average over different things, and these different things, where you take the expectation gives you different examples of normalizations, whether it is instance norm or batch norm or layer norm. So this depends on where you take these expectations. So you normalize across different channels, or you normalize across different inputs, or you normalize across different layers. So these are the different sort of things that you can potentially do. So you take the mean out. So you extract the mean that takes out the trend, and then you divide by the standard deviation. So this roughly forces things between -1 and 1. And of course, you make it learnable, right? So this is, there are some scale factors. So the scale factors G and H are the learnable scale factors, so that you learn how much of this inputs and outputs are to be modulated. Now in lead time conditioning, what we do is that we directly target this particular normalization, and we simply say that you feed in the time here. So you feed in the time here, and you make this learnable things as MLPs. So in other words, this GN, let me write down. Gn of t could be, for instance, sigma of some W of t plus b, something like this. So you have some weight factor. These are small neural networks, right? So small MLPs. And these are learnable parameters, of course. You learn them along the process so that you allow the machine learning algorithm to discover its own normalizations. So this is a very simple trick. Remember that every sort of machine deep learning architecture has these kind of normalizations, and you just condition them with time. That's why these are called conditional normalizations or time conditional normalizations. Okay, so what does it mean in practical terms? Now let me try to explain this through this picture here. So remember that all these layers, so for instance, if you take this layer, these are all independent layers, right? You do some convolutions, you do some nonlinearities, convolutions, nonlinearities, patching, concatenation, and so on. Each of these you can put in a time conditioning. So here you have a time conditioning here, a time conditioning here, time conditioning here, and so on. And similarly up here, you have to do a time conditioning, a time conditioning, a time conditioning, time conditioning, time conditioning. So you have an additional learnable element everywhere. Okay, so this is a simple way, an elegant way to imprint time across the entire neural network so that it learns that, at this instance, I still have to predict something, I have to do something, attribute or deduce attributes, compute features related to some sort of time dependent process, right? So this is a very useful trick, and later on in the numerical experiments, I'm going to illustrate how this is going to be useful. Okay, so you give time initially, but that is certainly not going to be enough. You give time as an input, as a sort of input at every layer through this layer normalize or through these normalizations. Okay, so this is going to be the key trick by which we can put time into the neural network. Is that clear? And if you have questions, of course, the interaction in a Zoom call is much limited, but you can always ask questions through the chat box, and I'll try to answer them. Okay, if not, let us try to see. So this is at the architecture level, at the model level, what we can do in order to put time into the mix, into the equation. But we can also do some things at the level of training. And let me try to explain that. So there are different kinds of training strategies that you can do. Let me try to explain at least two of them, which can be useful. And let's concentrate on that. So first we can do what is called one at a time training. What does it mean? So in this particular case, remember that whenever we have data, it's always in the form of these trajectories. So in other words, perhaps I can write it down here that you have trajectories. So let's say you have trajectory, and this is u at tk. Okay, this is k from 1 to capital K. So this is what is given to us. Whenever we have been given data, we have been given trajectories like this. Now I made a very simple assumption that across all the samples, across all the training samples, I have access to the solution at the same time point, which is okay when you're doing numerical simulations, which is perhaps not okay when you are, for instance, having to deal with observational data. If you have observational data, then you can sort of bring it. You can also deal with that. This is not limited to just having sampling at the same points. You can sample at different points. Okay, that's not going to be an issue. So what you do is, in this one at a time training, what you do is that during the training, you give as inputs your initial condition, which is u bar, which is given here, and you give the times tk. So you give them as, and then you get k samples per trajectory. In other words, let me write down the loss function. So the loss function L is equal to, L is now the loss function. It is not related to the differential operator, right? So it is 1 over k. Okay. Then you have the sum. This is little k from 1 to capital K of the output of your operator. So let me call it as S star. So you have u at tk, so some norm u at tk minus s star of tk u bar, some norm, okay, some norm over x. So remember that in space, we are assuming that these are functions, right? Of course, we have to discretize them further in space because, but in principle, the neural operator is able to deal with spatial inputs, which are continuous, right? So you have Reno and so on properties to take care of that. So what do I do here? Let me try to explain that. So I look at all these times tk, okay? And so this is the loss at the sample I. So this is the ith sample, right? So Li, and then of course the overall loss is also a summation over I from 1 to m of Li. So first of all, per sample, what you have to do is you look at the solution at different times, tk, you take the initial data, you output the solution, you compare the losses. And then you bin them together, add them together, and you sort of do the optimization over all samples. So as you can see here, if we have different sampling points, there is no issue, right? Because each of these losses are taken independently. So you can, of course, have different sampling points. So this is what is called one at a time training. So the advantage of this compared to before is that you have k training samples per trajectory, okay? And we will see that this can be a very effective strategy sometimes, that you just evaluate at different times. But this is not really taking out the full potential of the method, because the full potential of the method is by using what is called all-to-all training. So what is this all-to-all training? So remember that we have the trajectory, so we have this u of tk. So the idea now, and please concentrate on this point because it's an important point, is that what we are going to do is at the time of training, we are not only going to consider what happens when you take the solution from initial data to a given time, but we consider all the intermediate times. So perhaps it's not a bad idea to draw a picture and try to. So let me explain that at some. So one at a time is the following. So now let me draw the picture in the following manner. So we have 0, T1, T2, T3, like this up to tk, tk plus 1, up to capital tk. So imagine that at each of these points, you have been given a function, right? Because that's what we have, not a single vector or a single value, but a whole function. Then what we have in one at a time training is that you first give the initial value here. So this was u bar, and then you give, so you compute the solution at this time. So you do this, then you compute the solution at this time, then you compute the solution at this time, compute the solution at this time, and so on. Right? So these are the k versions of the trajectory, k applications of your operator, and then you sum them up the way I've just described them. So that is one at a time sampling. But what we want to do is something radically more sort of not complicated, but extensive. And this is all to all. What does that mean? So all to all, roughly speaking, is along the following lines. So, okay, so let me draw the picture here. So again, you have 0, you have T1, you have T2, tk, tk plus 1, blah, 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 right? All the intermediate times are given. So now, in addition to going from, so imagine that from 0, in principle, the solution operator can take you to T1, it can take you to T2, it can take you to T3, T4, and so on, just like we did before, right? But we also know that this is a semigroup. The solution of a time-dependent PDE is a semigroup. So in principle, if I'm sitting at T1, okay, I can go to T2 by just taking T1 minus T2 delta T as my time increment, right? But I can also go from T1 to T3 by having 2 times delta T as the time increment. I can go from T1 to T4. I can go from T1 to T5. All of this is possible. I can start at T1 and then go to T5 to T6 to T7. All of this is possible. Similarly, I can sit at Tk. I can't go back in time, right? There is causality. So time always has an arrow. You always go forward in time. You cannot go back, except if the problem is reversible. And this we don't know a priori whether the PDE is reversible or not. But just imagine that you are at Tk. So you can't go back, but you can go to tk plus 1. You can go to tk plus 1 with delta tk as the increment. You can go to tk plus 2, tk plus 3, so on, and finally up to T capital K. So all this is possible. So essentially from the initial conditions, you can go to all the time steps. From the first time step, you can go to the remaining K minus 1 time steps. For the second time step, you can go to the remaining K minus 2 time steps, and so on and so forth. So we are going to exploit this because this data is already given to us. It is very much there. So this is a smart idea that we came up with because this has not been considered in the literature. So essentially what you can do is that probably I have written down this here exactly. So if you start at a point Ti, you can go to any j which is greater than I. Okay. So in other words, if you start at tk, you can go to tk plus 1, tk plus 2, tk plus 3, and so on. You of course have to provide the lead times because that's the amount of time that it takes for the solution to evolve. And then you give the value of the solution there, right? So what is the advantage of this strategy? First of all, the data is there, right? Whenever you have been given a trajectory, you have been given all these data points. They're available to you. You don't have to scamper for the data. But the advantage is now we have a lot more data, right? Because remember that from the first point, from this point, we have access to K data, then K minus plus K minus 1 data, K minus 2 data points, and so on till 1. And this we know is that it's K plus 1 by 2, right? So instead of having linear, the data content in the trajectory earlier was just linear. So you had K training samples per trajectory. Now you have K square training samples per trajectory, right? So it's a dramatic augmentation of your data. And you do this for free in the sense that this data is already there, right? So the advantage of this all-to-all training is to be able to leverage this semi-group, this causality property of the solution operator. Okay, so that whenever you have been during training, what we are going to do is that we are going to take all these pairs, images or pictures or whatever you have, we are going to take all these pairs and then we are going to be able to access, we are going to use them for the training. So what is going to be the loss function? Now this is interesting. Perhaps it requires an expression. So the loss function, again, this is for the ith trajectory because you also have to sum over the trajectories, right? So ith trajectory. So you sum over, okay, perhaps lth maybe, L. So you do the following, okay? So you take u at tj, okay, minus s star. So this is your neural operator, which takes into account tj minus ti of u at ti. The data is given to you, so you generate the data and then you do the norm here over some function space x, and this is ij from 1 to capital K, I less than j. Okay, so this is the trick. So now what you can do is that you can take all these intermediate points, you use your neural operator. So in other words, give the neural operator the time t1 and ask it to generate the solution at time t2 and then compare using this method. Similarly, you take it at tk and ask it to compare it at tk plus 5. And then you bin it together, compute the loss function, and then of course, overall you have to sum over all the trajectories, right? So in addition to this, you also have to sum over all the trajectories. So the amount of data is quadratic in the number of time steps per trajectory, and it's also not quadratic, of course, it's linear in the number of trajectories. So let us imagine that we have 1,000 trajectories, which is nothing exceptional, and we have, let's say, 20 time steps, 20 saves that we have. Then per trajectory, we have 210, right? Because, yeah, 210 samples. And then in addition, we also have 1,000 trajectories. So we have 210,000 trajectories. So this allows us to augment our data seriously. And we need all this data. You'll see later on that this data is very, very important. Okay, so this is the basic principle behind this all-to-all training. Is that clear? This is sort of, it requires a little bit of concentration and it requires a little bit of thinking about how we are inputting the data, how we are outputting the data, and so on. Are there any questions, any first questions on this approach? You can either unmute yourself or you can ask through the chat box. No? Okay, think about it, and if there are any questions, you can, hopefully I'm better on Friday and I can come to class and then you can ask me the questions. Now, this is what happens at the level of training, that you take into account this additional data, this, let's say, quadratic in the number of saves, quadratic in the number of time steps per trajectory. And so remember that this is a complete contrast to what we had in the last lecture. So in the last lecture, we were just using the fact that per sample or per trajectory, we have exactly one sample because we are simply using endpoint evaluations. Now we have increased it by a factor of k squared, which is a lot more, right? So instead of 1,000 samples, we will have 210,000 samples. And this is an important point. Okay, there is a subtle point that I'm going to mention in a second. So what about the inference? At the time of inference, what do we do? The inference can be the way it has been set up, that it can be direct or it can be autoregressive. So let me try to explain this again. Maybe I have an additional page because it's important. Damn it. I didn't want that, did I? Okay. I wanted a blank page, no? Isn't this the one? Yeah. So what is what happens at the level of inference? So let's try to take this. So I have inference. So now you have this trained operator S star, and what can it take? It can take T and it can take Q, and it can produce what it wants to produce. Now your task is, let's say that you are, again, let me draw a picture. So you are starting at T equal to 0, and let's say that all that you are interested is at the solution at a later time T equal to T. Okay. You train the way you want to train, but what you want to infer is just a solution at a final time T. Now, there are different ways in which this can be done. The first thing that we can do is that you can do a direct evaluation, direct inference. What do I mean by that? So simply take S. So this is the U bar. So simply take this. Okay, it has been trained, but now at the level of inference, it just takes this value and it infers. So that is direct, and this can be effective. This is very cheap because it's only one evaluation of the neural operator. But of course, you can say, well, we have trained all to all. We have information about intermediate time points. Why don't we use that during inference? You can. So in that context, what you can do is you can choose. So this is autoregressive. Let's write it down. Autoregressive inference. So what you can do is you can start by doing one step autoregressive rollouts, right? So what does that mean? That you can you can apply star to T1 and then U bar. So you go from here to here, no problems. Then you apply again. So you take this as the input and take T2 minus T1, apply your operator. So that's the next rollout. Do here. Then you apply your operator once more, T3 minus T2, and you get the drift, right? So you can do this one step at a time, one step at a time. This is one possibility, that it's a 1-1-1 autoregressive rollout. But remember that the way my neural operator, time-dependent neural operator is set up, I don't have to do this. I can do any combination. In other words, let me try to explain that. Let's use another color, red. And I say that in the first step, I go 3 steps. I go here. So in other words, my operator would be, let's say, S star of T3 U bar. Okay. For some reason, I say, okay, I can go all the way. I can jump 3 steps. And in the next step, I can say I want to jump 5 steps or 4 steps or something like that. So I have my operator can output any solution, right? So then what I do is I take T7 minus T3, so it jumps 4 steps, and then it goes to S star, and so on and so forth, right? So you, of course, have to take finitely many steps so that you reach capital T, K steps. But so you can do any of these choices now. So we have the flexibility. So and this is at the level of inference. So we just have to check for ourselves. Of course, there's a price that we pay, right? Because in terms of the cost, there are 2 things here, cost and accuracy. So in terms of the cost, it is quite straightforward to see that the direct evaluation is the cheapest because I have to do one computation of the neural operator. But and this is the most expensive. Autoregressive is the most expensive. Autoregressive in the sense that all these steps, right? Because that will have to do k evaluations of the operator. And anything in between is between 1 and k. I can do 3, I can do 6, depending on what I want to do. But the accuracy is going to be very, very different, right? Because it could be that for a particular problem, and we will see examples of that, that direct, since you have to go far out, you are going to make more errors because it has to learn something much more complicated. Autoregressive is simpler because you just have to predict the next time step, and so on, but your error can accumulate. So oftentimes what happens is that something in between is the optimal strategy, as you will see in some of the numerical experiments. So this is a choice that is left to the user. By doing this kind of a training and by setting things up in this setup that I just explained, what we have is that we have multiple possibilities for autoregressive rollouts. And in particular, we can predict at any time because we can just give the lead time and we can predict. So in principle, we have a continuous time prediction. And this is often what is lacking because people can only make discrete time predictions, as I explained in the last lecture, but we can make continuous time predictions, in particular to what are called out of distribution times. So what do I mean by that? These are times that have not been seen during the training process. And I'll give you examples. Okay, so good. So we have a new training strategy, which sort of assimilates or accumulates data in a nice manner. And inference is based on, it gives you a lot of flexibility at the time of inference. And it allows us to learn the entire operator. Okay, now let us try to see how this works in practice. Okay, I'll delete some of this. So why do I have this? Because I wanted to show you a movie here. So all the results that I'm going to show today are based on the shear layer. So let me see if I can, I should have, no? Yeah, exactly. So this is a final time. I wanted to show at an earlier time. So again, let me show you what it is. So this is the x velocity. Of course, now I can't annotate. But on top is the x velocity, on bottom is the y velocity. And this is a movie. So this is what we are interested in. So, okay. So it plays. So you start with something and then the solution looks, particularly concentrate on the y velocity and see how much the solution has changed, right? I should have slowed down the movie. Now I realize that the movie should be slowed down. But you see that there is a lot of complex phenomena that is happening and there's a big change in terms of time. So you start from t equal to 0 and you go to t equal to 1, I think, in this particular case. Okay, so let's see what are the results. So this was the shear layer. The first thing that you do is to compute error versus time. Okay, so there are two plots here. And this plot is, this is the actual error. This is the number of training trajectories. Perhaps what is more interesting is this is a log-log plot. As you can see, this is log and log, or semi-log at least. So we have this, so we get a particular trend. But the important thing here is a number of training trajectories is what is being used. So we go all the way from 256 training trajectories to 8,192 training trajectories. And here we are just doing a direct evaluation. Means this is the training is one at a time training, not all to all, one at a time. So in practice, if you have 256 trajectories, I don't remember, I think there are like 10 saves or 10 snapshots here. So it is 2560 time steps. The important thing, there are two things here. First of all, as you, this is CNO, time condition CNO. The first thing, as you can see, is that as the amount of data increases, the error goes down in a very predictable manner. The rate is 0.33, means a very, very predictable, completely nice scaling. And what is very, very important here is that it's true for every time. So whether I want to evaluate at time t equal to 0.2 or all the way up to t equal to 1, I get the same kind of a scaling. What differs are the constants. Okay, so as you can see that as you go forward in time, so of course from 0 to 0.2, it's easier to predict and the error is going to be smaller. So for instance, if I take 1024 trajectories, it is 1% error for the first, for ZT 0.2, and it is going to be little less than 2% error for the 0.4. It is going to be something like 3% error for 0.5, 0.6. For 0.8, it is going to be a little 4% error, and then it is going to be something like 6% error. So if you look here, the error is going to increase somehow linearly, right? It's not going exponentially, it is going to increase linearly. So this tells you that this strategy works. You are able to scale with respect to the amount of training data. The error, of course, has to grow because it's harder to learn what happens at t equal to 1 than from the initial data than it is to learn at t equal to 0. And here the inference is direct. So this is one at a time training. Inference is direct. Just a base configuration. Okay, so it works as expected. And what is also interesting is that now we are able to sort of evaluate at times that have not been seen before. So for instance, you train that, so these were the data points that were given, 0.2, 0.4, 0.6, 0.8, and 1.0. But in between also, we were able to train it very nicely. In the beginning, there's a lot of error, of course, because remember that there's a very sharp transition, particularly in the y velocity. But other than that, even though 0.5 was never seen during the training, it is able to predict the solution at 0.5. The same with 0.7. It was never seen during the training. It's able to predict that, and so on and so forth. So it does, it's a continuous prediction in time, not just a discrete prediction. Okay, so then these are the different training strategies, or no, this is the different inference strategies. So remember that the simplest is, of course, direct. As expected, it gave you whatever results that it gave you. So this is inference strategies. So this is what I explained just before I went into the numerical results section, right? So I explained these different kinds of inference strategies, whether we do direct, whether we do autoregressive, and what kind of autoregressive rollouts we can do. Okay, so here, as you can see, direct was not as efficient as, so autoregressive, this is one-step rollout. So 10 times 1 means, so we want to predict the solution in 10 saves, not 10 time steps, but 10 snapshots. So what we do is that we first go from 0 to 1, 1 to 2, 2 to 4, 2 to 3, and so on from 9 to 10. So already you can see that the orange is better than this one. Of course, this is more expensive, but perhaps the orange is more expensive than blue, but perhaps the inference costs are not considered that seriously. And then, as I said, we can go different ways. It has slightly better scaling properties though, so eventually maybe it will catch up. But as you can see, we have different kinds of strategies that we can take. So we can take 2 jumps, right? We can go from 0 to 5, then 5 to 10. This gives you the answer here, not as good. But then, as you can see, the 2 which are better are somehow intermediate. For instance, this one, the green one, it takes 1 time step in the beginning. And this is to take into account that there's a fast transition in the solution. Things happen much more quickly in the beginning. And then the heuristic is that they happen more slowly. So it goes 1 time step, and then 3 to 4, then 3 more to 7, and then 3 more to 10. And this gives you the best results. And the training is exactly the same. It's the same neural operator. It's just by doing a slightly different form of inference, you can see that you can bring down the solution quite a bit. For instance, let's look at this one. So this is 1024 trajectories. Okay, so somewhere here is the solution, I guess. And this is the corresponding one here, the direct evaluation. And as you can see, so this was like, I don't know, 6%, and this one is more like less than 2% even. So by a factor of 3, you bring down the error simply by using a different heuristic. You have some knowledge of the solution, and you use that to have this heuristic evaluation, okay? Similarly, another strategy that one could use was to go 5 times in the beginning, and then 2 and 3, and that also seemed to be effective. This I have no heuristic explanation. I can understand why the green is better than the orange and the blue, but I don't have any reasons to understand why the red is better than the other things, but this is how it is. So the idea is to tell you that there is a variety, there is a choice that you can do at the level of inference, okay? And then I want to go for the break by talking about different training strategies. So these are training. Okay, so remember that, T1 is one at a time, and T2 is all to all. And as you can see, there are different inference strategies. So T1 and T2 are represented here. As you can see that there is a consistent gain because you simply have more data. So with the all to all, you get a big gain, or not a big gain, but a gain nevertheless, right? As you can see, for the same number of training trajectories, one is consistently better than the other. And if you sort of couple this together with an autoregressive rollout, this is 442, then you can see very clearly that there is a significant gain. So for instance, with 2048 trajectories, you can go down from about 5% to 2.5% or something like that, right? So this really pays off. And of course, the training is more expensive now because you're taking into account more data points. So the training is going to be more expensive. But this is the strategy that we are going to leverage from now onwards, that we are going to train all to all. And in terms of inference, we can either do direct or we can do autoregressive, depending on the context that we are. Okay, so this is what I wanted to say with respect to time-dependent operators. Just to summarize, just by putting in time conditioning into the architecture, we have been able to predict the solution, not just at any point in space. That was the whole point about Reno and neural operators, but at any point in time. We have been able to leverage the fact that it's a time-dependent problem, there is causality and so on, in order to be able to predict, in order to be able to use more training data. And we have also been able to leverage that to have inventive autoregressive rollouts. Okay, so with that, I stop here and let's meet at 10 past, 12 minutes break. And then from there, we change gears a little bit and we try to solve some of the other problems that we saw with neural operators. Okay, see you in a bit. Hello, are people back? Yeah, so I can only see David, but okay, let's anyway start. Hopefully people will be back soon. So during the break, there was a nice question by Luca Gaffarpour. So Luca asked, is the all-to-all training strategy and autoregressive inference technique specific to CNOs? Or can it be extended to any time-dependent neural operator? So yes, it has nothing to do with the spatial structure of the neural operator. All this is true for any neural operator because all neural operators, whether it's FNO, CNO, DeepNet, and so on, these all use different kinds of normalization layers, and you just put time into those normalization layers exactly in the method that I described. So this strategy and the all-to-all is at the level of data and the loss function. So it has nothing to do with the specifics of the neural operator that you are training. So this is going to be as generic as you get. Also, do we see similar error scaling as we saw in the shear layer benchmarks? Yes, in all problems, we have evidence of this kind of scaling. Of course, the exponents are going to be the constants. The rates are going to be very different. The constants are going to be very different and are problem specific. But the qualitative picture is exactly the same. That there is always consistent scaling. And what I showed in the last slide is absolutely holds. Okay. So with that answer to that question, which was a very relevant one, let me move to the next topic essentially. And let me start by reminding you some of the issues that we started off with, right? So we had these three issues that we identified: data on non-uniform grids. I gave you some ideas, but I don't know if you'll have time to address them. Time-dependent problems is something that we addressed now. And the last point is this concept of scaling with data, means how much of data is enough data, right? And let's start with that. So in some sense, the fact what I presented here are different ways in which we are able to add data to scale better with data and so on. But this is still the key issue, that the key is going to be the scaling. And we know that whether we take the time-dependent version or not, we have very consistent scaling rules. So this was again the shear layer, but just without the time-dependent version, just end time prediction. And you saw that there were these different rates. Here also you saw that there were different rates. Where was the picture that I did? Different rates. So the question that comes in is automatically, can we improve the rates? Okay. So the key somehow is indeed scaling. So the question is, so then given that we have this context, this background, the correct model or the model that we need to use is the one that scales the best, right? Means in the sense that if you provide it enough data, it should have the best performance in some sense. And this is what has been understood now for the last 2-3 years in the machine learning community, not just for scientific machine learning for scientific problems, but machine learning for vision, for text, and so on and so forth. And this idea came essentially from language modeling, because text, NLP, whatever you call it, NLP, natural language processing, where people realized that the key to everything is scaling. And this happened around 2020, 2021. So there's a very influential paper of Jared Kaplan et al. At that time at OpenAI, these people moved to Anthropic now, but this was around 2020. And they discovered something which is interesting and fundamental. And that is what I'm showing you here. So this was not about not about the kind of problems that we are dealing with. It's about just language. It's about modeling natural languages, right? And the idea of Kaplan et al. Was the following: that they just took so in language is also somehow a recurrent task. So let's say that LSTMs, RNNs were sort of state of the art in, let's say, 2017, 2018, and so on. And the point is, so these are the number of, this is the loss, and this is how things scale, right? With respect to model size, with respect to data, and so on. And they observed that LSTMs scaled, but they scaled very slowly, and they were saturated very, very quickly. And the architecture that managed to sort of beat this was transformers. Okay. So essentially from this Kaplan et al. Paper, so this is Kaplan et al. This, all that they did is that they took a bunch of models and they took a bunch of tasks and they studied how things change when you increase model size and when you increase the amount of data. And these people became famous. Jared Kaplan recently was even profiled in New York Times, so so it's sort of, so what are the observations? So essentially what they did is, for natural language, they tried to study scaling with respect to data, with respect to model size, and somehow data and model size together, they constitute compute, right? Because during training, now we are not even talking about inference, but during training, you have to loop over all the available data. So, you do through batches, and in each batch, you have to loop over some set of the data. Then the next batch, you loop over another set of the data, and so on and so forth. So somehow the compute is roughly the product. It's not exactly, and it's roughly the product of data versus model size. And their discovery was that compared to all architectures, so there was, first of all, there was consistent scaling. There's no reason for it. There's always consistent scaling. The exponents, of course, the rates, the constants, they change in different settings. There is no universality in terms of the rate, but the quantitative feature is exactly the same. So the idea is that this problem will be solved in some sense if we take large enough models with large enough data, right? So that's and this is the beginning of LLMs, the beginning of large vision models, and so on and so forth. People understood that they have to scale up their models. And as you saw in my previous lecture, also in the lecture before, first hour of today's lecture, we observed similar kind of scaling rules with what we are doing, right? So that realization has also caught on to us, but let's say 3-4 years later. So there is consistent scaling. And the most important thing is that among all these architectures, at least for language modeling, transformers, they really shine in terms of they have scale better. So this was sort of compared to other architectures, right? So transformers are going to scale better. If you have more data, you have better model size, they're able to scale, they're able to use the information, the compute better, right? So this kind of considerations which are there in language modeling, coupled with the observations that we saw in the last couple of lectures, that there is this consistent scaling, that inspires us to move towards transformers. Okay, so this is just a representation of transformers. And today and in the next lecture, potentially in the lecture next week, also to some extent, I'm going to give you at least a beginning, an input, a feel for what transformers can do in this particular world. Okay, and it can't be arbitrary transformers because you saw that with this Galerkin transformer, it didn't really scale, right? So what's the principle here? So we change gears. So the basis of transformers is something called attention. Many of you might have at least read it in the media that transformers are all based on a mechanism, on a mathematical object called attention. And this came in 2017 with this very influential paper from Google, Vaswani et al., which told us that, okay, there is a different way of processing inputs and outputs of neural networks. And let me explain it in terms of discrete objects. And later on, I'm also going to explain it in terms of functions. Because everything that can be done at a discrete level can be sort of lifted up to the level of functions. So what is the principle of attention? So first of all, let's imagine that, so the point is we think in terms of sequences, and attention or transformers, they were introduced for sequence modeling, but we can convert our problems to a sequence modeling problem very easily. So think of your input in terms of an input sequence. So this is a sequence. Think of a one-dimensional function. Perhaps that's the easiest to understand. Okay, and what is the input? So the input is going to be a vector v. Okay, and so this is v1, v2, all the way up to v capital K. So think of discretization of a one-dimensional function, right? And each of this is a vector of n dimensions or n features. So you have, for instance, a one-dimensional vector function discretized at different points in space. It's a very, very simple understanding. So what convolutions would do, this is what we have looked at so far in CNO and FNO. I am not seeing any shared screen. Someone is complaining that people can see the screen, right? Yeah, it seems that everyone can see the screen. Okay.
Can see it.
You can see it, right? Then the whole lecture would have been redundant. Okay, just check it for yourself. What's the situation? So remember, now pay attention to this, pay attention to attention. So what you do in CNO or FNO is you do convolutions. So what would have been convolutions is you take a kernel of a fixed size and then you apply the kernel to bunches of these points, right? First to the first 3 points, next to the next 3 points, next to the next 3 points, and so on. But the self-attention is completely different from that. So what you do here is that you are not going to sort of scroll through, you're not going to plow through the entire sequence by using discrete blocks. Rather, you're going to study the cumulative effect of each of these features. These are sometimes called tokens, okay? And from language modeling, these are called tokens. So each of these features, so VK is the kth token, because it came from language modeling, but think of it as the value at a certain point, right? So what we are going to do is we are going to define a matrix in this case, or a function in this case, not a matrix valued function, such that the following mechanism works. And maybe the best is to explain what goes on. Perhaps I need to blank, yeah. Perhaps I need to explain it on a piece of paper. So remember what we are doing now. So we have, so these are your tokens. So you have V1, V2, V3, V4, and so on, V5, V6, so on. So what you do now is that you are going to study the cumulative effect of all of them together. So in other words, you can see, unlike a convolution, you're going to see what is the effect of V1 to V2, V1 to V3, V1 to V4, V1 to V5, V2, just like all to all, right? V2 to V3, V2 to V4, V2 to V5. You are going to study these correlations in some sense. And how do you study these correlations? There is a particular method, there is a particular sort of throughput through which you study. So what you do is that now we have to be a bit careful about defining different things here. Okay, so the first thing that we are going to do is that we are going to fix, so this is the output of the attention function, A of V. So we are going to look at the result of this attention at the kth point. So this is going to be your UK. And there are several elements to it. So first element is that we are going to sum over the contributions that are made by all the points to this point. Okay, the information that is the correlations, the information that is carried over from all the points to this point. So we are going to attend to this point from all the other points. That's why there is a sum over all the other tokens. Okay. So the information, it's not like a convolution, because in a convolution, only the information from the nearby points is going to be taken into account. Here, on the other hand, the information from all the points is going to be taken into account. Okay, this is an important issue to mention here. And how is this taken into account? So first of all, there are three objects here, three matrices, query, key, and value. Okay, these are again nomenclature from natural language processing, but why these things come about is not important to our context. We just have to remember that these are matrices. These are matrices of a certain size. They don't depend on the token itself. So remember, the size of all these matrices is fixed. So it is so they have n columns and they have m rows. So what is n? N is your feature dimension. Remember that each of these tokens has n features, right? So that's your feature dimension. And m is what is called an embedding dimension or an attention dimension or whatever, key query value dimension. So this is a sort of an internal representation dimension, okay? So for instance, n can be 10 and m can be 20. Means this is a hyperparameter that you're going to choose. It is independent of the number of tokens. And this is the most important thing. So for all the tokens, you're going to have the same objects that are going to come in. So you're going to compute, these are learnable matrices. So at each point, so remember that I'm going to update the value or update the input at this particular point k. So what I'm going to do is that I'm going to loop over, I'm going to sum over all the points v1, v2, all the way up to v capital K. And what I do is that at each of these points, I compute the value. So this is a matrix vector multiply each of these points. So at v1, I compute the value v of v1, v of v2, and so on. And each of these points, I compute the key, the same principle here, k of vj, I compute the key. And then comes the interesting part of attention. So far, so good. But as you can see that here, I don't put a k, I compute the query. So essentially what you do, again, coming back to the picture here, is that at all these points, so I have, I compute v of v1, v of v2, all the way v of, this is very bad. Okay, so v of v capital K. Similarly, I want to compute the keys here, k of v1, k of v2, k of capital Vk. But I also compute the queries. So q of v1, q of v2, and so on, q of vk. Now, what I'm going to do is that I fix the jth entry. So I have k of pj, and then I do a all to one broadcast. Okay. So in other words, I compute this in a product q of v1, k of vj, q of v2, k of vj, and this is your fixed j. So now when you move j, you can see that there is this quadratic multiplication, q of vk, k of vj. So what we're going to do is that at each point, so there are two loops here, right? So first, in the outer loop, you're going to fix my j and you're going to sum over j. And then there is an inner loop here. In the inner loop, what you're going to do is that you're going to compute the query at all the points, all the other points here. So in other words, I'm interested in computing here. I fix this point and I do all the loops, and then I compute all these values. And then what I do is that I do a softmax. So all of you might have seen softmax. Softmax is a way in which I can convert a vector into a vector of arbitrary entries into a vector of probabilities simply by taking a weighted exponential. So in other words, what am I doing here? So what I'm doing here essentially is that so there are two loops, as I said. So perhaps I add another, sorry. I add another blank page. So there are two loops, as I said. So maybe I put this. Okay. So at the end of the day, I'm interested in computing the value at this point. Let's call it as k. Okay, little k. And what I do in the outer loop is I look at all the values. So okay, something like this. So in the outer loop, I'm going to fix, let's use another color, let's say J. So I'm going to fix this J and I'm going to sort of sum over all of these J's, okay? Then there's another third loop, which is the inner loop here, which is given by, so now I have fixed J. It's the same vector, something like this, right? Something like this. Now I fix J, and then what I'm going to loop over is all these points. So I compute the queries and I do this kind of a broadcast. Similarly here, here. So essentially what you do is that this guy here, this operation here is the key point of attention. This is a scaled dot product. You'll see in the next lecture that we can take another function or different other functions. It's a scaled dot product. What it tells us is the effect on the value on the token, the jth token from the kth token, a relative effect, right? Because we are taking sort of a softmax over all the possible values. So we are taking the relative effect. Okay, so what is the computation then? The computation is that in order to find the value here, I'm going to sum over all these points. Okay, especially the jth point. So this tells you the relative contribution of each of the surrounding tokens, including the token itself, right? So there is also self-attention, including the token itself. From all the, it receives information from all the other tokens, but the information that it receives from all the other tokens also involves a further loop where this information is weighted by the relative contributions of each token, right? So this is why, so you can see that there are k elements, k operations here and k operations here. So there's this entire mechanism is going to be quadratic, okay? So when I show you the functional version of it, it's probably going to be clearer. Softmax is just one way of, so this is telling you the weighted average of the information. So what is attention? Attention tells you that, to make some update at this point, how do I take into account, accumulate information from other points in a smart manner? So heuristically, it is not a very, very difficult concept at all. Okay. And then finally, all this gives you matrices, which are m cross n. So you have to come back to n times n matrix. So then you have an output matrix, which is given here. Okay. So it's all based on some very simple matrix operations. It is independent of the number of tokens. So you can take whatever tokens you want because this learnable matrices Q, K, W, and V, these are arbitrary. So there is no particular sort of structure to them in the sense that these are only dependent on the feature dimension and on this embedding dimension M. And you should also think about why this is permutation invariant, because there is no ordering here. So I can just jumble these things together and I will get back the same value. Okay, perhaps this will become clearer when I look at it from a function perspective. So at this level, at the vector level, is where you implement things. So you have to compute essentially these two different loops where you compute this query key and value vectors and you do a softmax. And you can understand it very well from, okay, perhaps I explain this here as a neural operator. Maybe it falls better in our yardstick, okay? So again, the same principle. So your input now is a function. It could be in arbitrary dimensions, but let's say for simplicity, I'm in one dimension. Things are simpler then. The geometry is exactly the same. And then what is attention? Attention can be thought of in these terms, okay? It looks ugly, but that is what it is. So what am I doing? So now let's think in terms of functions. So I have a function here, which has been given its different values at different points. So as you can see that there are two loops or two sums, or in this case, they get converted into two integrals. You have an outer integral, which is in y. So these are all the other points. So how do I do this? Maybe again, I had blank paper. So let's for simplicity do it like this. So you have 0 to 1, let's say, and you have a fixed number of points that you have discretized in. At each of these points, you have, let's take 3 of these, right? Because, okay, let's, I don't know how to copy it because I think there is a function by which I can copy this thing. It takes me longer to copy than to write. Okay, so this is your input V, right? So your input is here. So these are called VK. So this is XK, VK is sitting here. So in the there are two integrals. So first is the outer integral. The outer integral is taken over Y. So the effect over Y is computed. So in other words, what I'm going to do is to integrate here. So which means that I take all these guys and evaluate them at this point. Okay. And then in addition, I have this inner integral. So this is where the softmax comes in. The softmax has just been rewritten in this form. So at each point Y, so I'm integrating over Y. At each point Y, I compute the value. I compute the key, okay? But I also have to compute the key. I also compute the key here. But I compute the query at every other point Z. So this is the second integral. So this is the integral over Y. This is the integral over Z, okay? So I have to compute the key, the query, sorry, Q at all these points, and I fix Y here. So I have to broadcast up to here. So there are these two loops that are there. Okay. So as you can see that this is a weighted sum of a weighted integral. There is an inner integral that gives you the weighting, and there's an outer integral which provides you the sum overall. Okay. And then W is also some fixed matrix. All the while this Q, K, and W and V, these are sort of fixed matrices. So this is sort of a functional, so given a function, attention can be interpreted as operating on functions rather than as vectors. Means the way to link them is to simply take a uniform grid and pass to the limit. And this is indeed what you're going to derive. Okay. In other words, if you think of it, so what happens is that in terms of operators, so this is operator attention. So you can think of it as a kernel. Okay. So this is an integral. So you can think of it as a kernel. But now the kernel is going to be nonlinear. Okay, so this is a kernel K, which takes values at X and Y, as you can see, but the kernel itself is nonlinear. So the kernel is here, so this is capital K. Let me drink some water. Okay, so the kernel itself is nonlinear, and this is going to be the big difference that we had before. Because if you think of FNO, CNO, and so on and so forth, so there also these were kernel integral operators. Remember that we had changed the matrix vector multipliers into kernel integral operators, especially with this translation invariant kernels. That's why these were convolutions. But this was linear. Okay. Now what we do is that we do something which is non-linear. So this is sort of the strength of this method in some sense, that your kernel is also being trained based not just on it's also being trained not just the kernel dimensions, but the kernel structure, but also the kernel itself is being trained depending on this nonlinear data points. Okay, so this is sort of the essentially, if you want to think of attention itself, you can think in terms of this particular integral. So what does it do? It takes relative contributions. So there's a kernel. So this guy here is a kernel, and what the kernel does is that it provides data-dependent relative contributions to the point Y, or to the value at the point Y. Okay, so of course it's in that sense a very, very powerful method, because now what you're doing is that you have a kernel which takes into account the data that you are giving, and it provides you relative information or relative weighting. Okay, so you expect this to be a powerful method from that perspective, because you're getting information from all the points in a data dependent manner, rather than in a fixed manner like you do. So first of all, compared to convolutions, you don't have any locality anymore, right? Convolutions had locality. This is much more global in nature. And second, it is non-linear. It is sort of data dependent in nature. So hopefully this is a good thing. Of course, there's a price that we are going to pay, which I'm going to talk about in a second. So this is at the level of the continuous function, at the level of the discrete function at which we implement. This is the formula. Okay. So of course this is a new object. So think about it, and I think maybe in the next tutorial they are going to introduce some vision transformers, and they're going to walk you through how this is done in practice. Are there any questions so far? This is a completely new concept. So if you have any questions, feel free to ask so that I can also see for myself whether you have understood or not, right? Because otherwise I don't see your faces. So it's impossible for me to. Are there any questions? Okay, if not, please feel free to ask in the next lecture so that by that time you have seen these objects and then you have understood. So again, I repeat, this is, you are essentially doing a kernel operation just like in convolution, except that your kernel is global and it takes into account every other point in the domain. But now you take into account, you do this in a data dependent way. So the weighting is based on actual values of the data, of course, in some latent spaces because you're learning representations. So this is the one of the ways in which you can think of attention. Usually people don't have it in textbooks. They operate at this level, not at this level, right? But this is where we from operator learning can understand this. So transformer is very much a neural operator. Whether it's a Reno or not is a different question, but at the moment it is it's certainly a neural operator in the sense that it takes functions as inputs and it churns out functions as outputs. Of course, there are many things that you can do which are done in practice, and let me just walk you through them. The first thing is you can do what is called multi-head. Okay, so now a single head would have been just this operation. But people are not just content with that. They say, aha, there's no reason why there should be only one route in which this information is being parsed. It can be parsed in different ways. So they introduce multi-head. So multi-head is essentially now you can see that for each head, so H is the head. Again, the notation comes from natural language processing, but it's a very simple sort of sum over different groups essentially. So now the value, query, and key, these things are dependent on the number of on the head dimension on the head, and then you sum over each head. Okay, so that's all that is happening. So instead of having a single way in which attention is being done, what you do is that you have multiple ways in which you put attention and then you accumulate them all together. Okay, so this is a generalization. And this can be seen, of course, from an operator perspective. So from an operator perspective, all that you have to do is to add some H dependence and take a sum. This is not an integral. You just take a sum. So multiple heads is just multiple ways in which you take into account this relative information. And in practice, people have to take multiple heads. Okay, so typically, I think in the large language models, they take anything between 10 and 20, 30 heads. This is an easy way in which you can scale up your compute. So, and there is an intuitive reason why this will be better because you have multiple routes, multiple channels through which information can be processed. So that's the first thing that you can do. The second thing that you can do is that attention is not that easy. There are many other. So first, so this is what is typically called a transformer block. It has many different ingredients. So this is what I have already shown you, what is multi-head attention. But there are also different normalizations, skip connections, feed-forward networks, normalizations, skip connections, and so on. Let me try to explain that in the next slide. So there's a very important point, and it again comes back to the first hour of today's lecture, which is about normalization. Means remember that all the time we want the inputs to each block to be roughly between minus and 1 to be scaled, right? So for transformers, almost always the right kind of normalization is layer normalization. So what is layer normalization? So layer norm is, and I interpret it as a function because we can view things in terms of functions. So you've been given some input features, n-dimensional input features. So it's a mapping between n-dimensional vector and n-dimensional vector. All that it does is that you have some learned scale parameters, alpha and beta. So this is a pointwise product. Pointwise product. So you take out the mean and you divide by the standard deviation. Okay. And the mean and the standard deviation are simply over the features, over the channels. Okay. So in other words, if you think of an attention layer, whatever the output of the attention layer is coming out, whatever the output is coming out, all that you do is that so this has different input features. Again, it's independent of the tokens that you are getting, right? So for every token, you do this normalization by itself. So you just average over the channels. Okay. And it is a very simple operator. All that you do is that it's independent. Different tokens are independent. So of course, as a function of space, you take a vector Vx and you just layer normalize it. So this is layer normalization. What it provides is that information across different channels is normalized. Across tokens, it can still be different. So this is a very simple operation, and it is almost universally used in transformers, right? So when we want to use our neural operators, what we do is that we will make this alpha and beta time dependent. So alpha of t and beta of t. And you can imagine that these are always initialized. Alpha is initialized around 1 and beta is initialized around 0 during training. So that is one thing. And then we need some MLPs. We need some feed forward. And again, I will give you an operator interpretation. So you have your feature input vector is V, which is in Rn. And then all that you do is pointwise. Now this is totally pointwise. You take this Rn dimensional vector, you multiply with the D times N matrix. So just like you do with an MLP, you add a bias vector, which is D-dimensional. And then what you end up, and then you have another one to normalize. So this is N cross D. So these are very local operations. So for every token, you have this MLP, and this is pointwise. You do it across all the tokens and you share the weights, of course. So this is some featureization across each of these domains. So it's a very straightforward operation. And then we have everything that we need. So we have this operator transformer block, which is given here. So this is a sequence of operations. So you start with your input function, V. Okay, this is, for instance, on a grid. Then the first thing that you do is that you use multi-head self-attention, MSA. So you start with V. This will give you your U bar. We have interpreted this as an operator. So you attend to the values at different points. Then you do a normalization, a layer norm. First you add, of course, you have a skip connection. So you take V, you have U bar, and then you do a layer norm. So you add. So there's a skip connection which allows for good gradient propagation. Then you do an MLP. So you take this, you do an MLP. This is the pointwise operation that I have already explained to you. And once you have an MLP, then you do the same. So you add the remainder, the residual, with the new input, and you do another layer. And you stack several of these blocks together. So this is the structure of a transformer. Okay. This is the main building block of a transformer. Is that clear? So you start with attention, you have some layer normalizations, some MLPs, and so on. Okay, so the MLPs are to give you some, and one, okay, perhaps I should have explained it. So remember that at the end of the day, you need nonlinearities to be very general, right? Because without this sort of ReLU type or your nonlinearities need to be something like this in order to be able to universally approximate functions. Unfortunately, if you would have just taken the self-attention, where is the if you take the self-attention, the only nonlinear processing that goes on is through the softmax, right? Now, softmax by itself is not good enough to provide you universal approximation, because you can ask, why do you need an MLP? So softmax is not good enough. You need softmax. What it does is that it provides some spatial mixing. Things are mixed in space, but you still need to do some universal approximation pointwise. And that's why the simplest thing is to put in a ReLU or a GeLU or whatever function that you have. So the MLP, the nonlinearity in the MLP comes from there. Why is the last residual connection? We add the result of U bar and not the normalized version you had. So there's a question from Lorenzo. What is he asking? I don't understand. U bar. So he's saying that why do we add the result U bar? What is U bar now? Okay, this is a mistake. You're right, Lorenzo. It is U hat. Yeah. So I'll correct the mistake. It is U hat, means it was just a typo. So what you do is that here you have U hat, right? So you have U hat, And this is the object that is added. Okay, so thanks for pointing out there was a typo there. Okay, it's not you, but it's you have. Good. So then that clarifies it. But there is a slight twist here, which is that. So remember that, and this is the last point that I'll mention, and then in the next lecture we'll continue with transformers. That all these objects, these are permutation invariant, right? Because there is no notion of space here. So for instance, self-attention, I could have reordered things whatever way. If you remember, in self-attention means there is no sense of location here, because I could have just reordered things in a permutation invariant manner and I would have gotten the same output. So everything else is applied pointwise. So the notion of mixing here, spatial mixing, is completely sort of position independent. Okay, so there is no sense of position, and this is problematic. So in other words, whether I give this as my input, means the values this as my input, or something else as my input, I just transpose these guys, put them in some random order. So this is meant to be permutation invariant, right? I get the same answer. So the sense of location is completely gone, right? So what we have to do in order to understand this is we have to encode the position, and we have to add something called positional encodings. Okay, so this is a very, very key part of transformer architectures. You have to take into account position. So let me try to explain this in a discrete manner, because this is where it is implemented. So what you do is, so remember, let's try to think in terms of tokens. So we have no sense of position now. So all of these are position independent, V1, V2, V3, up to Vk, and so on and so forth. So now we have a k dimensional input space, right? K number of tokens, and we have no sense of position. So what do? We introduce a sense of position by introducing the basis vectors, Ek. So these are the so-called one-hot vectors. So Ek is going to be 0, 0, 0, 1, 0, something like this. So in addition to this, I have another input, which is capital K dimensional. So let me explain that. So each of the token, okay, this is a very poor drawing, but here you also have Ek. So you have an n-dimensional input feature here. You have a capital K dimensional input feature here. So this automatically tells you essentially that this guy here is located at the kth location. So it's sort of an absolute coordinate system that you're providing with the token. This guy here is the third location. This guy here is the capital Kth location, and so on. So it provides you some sense of some notion of position. And then, of course, you use some MLPs in order to lift it, into the right kind of dimensions. So in other words, we want, so now our input features are n-dimensional from the actual features and capital K dimensional from the position. So what we are going to do is, I don't understand why I didn't I don't even know why I said it's D bar. It's there's a mistake. It should be, so replace the D bar with K, with capital K. Sorry, again, I will correct this in the corrected slides. So D bar should be replaced with capital K here. Okay. So what you do is that you just take this. No, sorry. What am I talking about? There is a mistake. Let me correct the mistake. So the N here is a capital K. So this is correct. So WE is D cross A K. So you take something which is K dimensional, represent it with D, and then bring it back to N dimension. Sorry, so I was correct. I'm sick, so I'm not completely following what I'm doing. But this is correct. So this will give you a learned n-dimensional embedding of the, or encoding of the position, and this will give you another learned n-dimensional embedding of the features. So this is a very general way in which position can be encoded. But in the original paper, they did not even use this kind of learned, they used the learned encodings, and they said, learned encodings are no better than just using fixed encodings. So fixed encodings essentially is a sine cosine representation of the location number K. So they just say, okay, the location number K is represented by sine of K over something. Okay, so you can think of this as a simplification of position encoding. So we need to provide these positional encodings, so the sense of position is provided in some form or the other. And this gives you the final version of a transformer block, where you have your inputs and then you have the positional encoding, which and together you go through multi-head attention, you do a layer normalization, MLP, layer normalization, and every time you have skipped connections. Okay, so this is sort of the basic architecture of transformers. Of course, there are some caveats, but this is what we are going to do in the next lecture. So I think I stop here. We have almost we finished almost the allocated time. Are there any questions? No. So hopefully on Friday I come in person, and if you have any questions, you can always ask me there. Okay, I will correct the typos and I will send the corrected slides, which will be uploaded in due time. See you hopefully on Friday. Take care. Bye bye.